Hello engineers. Okay, so now we are going to start analog circuit design. Till now we cover the network and RC, and I hope if you know a network and RC, you will be comfortable in analog circuit design. Means you can understand what is the node voltage, what will be the current focusing here. Okay, so firstly, whenever you are going for a circuit design, you must know that what is the ASIC design flow. The ASIC design flow will define you, okay, what will be the flow and how that analog circuit designer or analog design worker work in this domain. Okay, so let's start with the basic understanding of ASIC design flow. And most of the companies start the interview from this point. What is the ASIC design flow? Please explain the ASIC design flow. What is the steps you will follow? So let's start with the very basic fundamental, that design specification. Okay, this is a ASIC design flow. I'm starting this part. Okay, and I divide this in this way. Okay, this is an analog circuit designer part, and this is a layout designer. This is analog layout or layout. Layout have a category, that custom layout, full custom layout, a memory layout, standard cell layout. Okay, so you can configure in terms of layout here, but here that is an analog circuit design. Okay. So let's start with a very basic, that the first part is design specification. Okay, whenever you are in company and you have a 13, 14 year experience and you are a leader of that. Okay, so in analog circuit design, so of course that you have a some specification that market want something like you, that Aman Gupta are working on a that is OnePlus. Okay, so OnePlus have a requirement of some modification in terms of amplifier or something like this, that they are using a comparator or amplifier, op amp. So they require some specification. So in this specification, in design specification, you have a technology parameter, like a, you have a 45 nanometer or 90 nanometer, or you have a 180 nanometer. So of course you have a technology parameter. So let's start with the design specification. So I am just explaining in this way. Okay, what is happening? Okay, oh, what is happening here? Design specification. So in a design specification, I am just understanding in a way ki, okay, you have a basic understanding of op amp, just like in a BTech you must have a basic knowledge of ideal op amp. So whenever you are designing something, you have a specification. Just think in a way ki you are designing a op amp as per the requirement of the company. Okay, and that they must have a some specification, like they have a technology parameter, tech node. Okay, they must have a technology parameters ki, okay, you will work on TSMC 65 nanometer or 45 nanometer or 90 nanometer. Okay, as per the tech node. And then you go for, okay, what is the power dissipation? Okay, that power dissipation. Okay, on the basis of the power dissipation you can determine is current. Why? Because VDD is equal to that power dissipation is equal to VDD into ID na. So if you know power dissipation and you know the what is the VDD voltage, the supply voltage, you can determine what is the drain current. So you can bias with the current mirror. Okay, so this is a drain power dissipation. Okay, it will help you to configure your circuit. Okay, what is the basic? You have a specification. On the basics of the specification, you can define. Okay, this is the ID. Okay, this will be a tech node. Okay, that will be let that what is the bandwidth. Okay, that of course you are designing an amplifier. Some of course it have a bandwidth. What is the bandwidth, that 100 megahertz or 32 megahertz or 60 megahertz, this way. And that fourth one is gain. Okay, what is the DC gain? DC gain means what is the that lower frequency gain at possible. Okay, so 60 dB, 70 dB. Okay, so that is the information you have. So in a design specification, whenever you are entering a VLSI as an analog circuit designer, always you have a specification in terms of some values, like you have a tech node, you have a power dissipation. Okay, you have a slew rate also. You can think in a way. Okay, that slew rate, that 5 volt per microsecond or 10 volt per microsecond. Okay, So they will represent that some values. On the basis of that value you will set, what you will set, you will set that uh, powers, that id drain current. On the basis of that you will set that that what is your output impedance or what will be your gain. On the basis of the gain you can determine what is the transconductance gm, what is your operating point. Okay, so these are the very important points. On the basis of that you can decide the w by l also. Okay, so this will help you to design your circuit, and on the basis of the requirement you will set the w by l and transconductance and the drain current. Okay, so this is the very important part. So this is the one of that point, that when once that company is started, that analog circuit have a some design specification. After the specification you have a schematic design. Okay, once you have a specification, on the basis of the specification you will design a schematic. And if you design a schematic, so that schematic you designer, if you talk about the cadence, because I have a work on cadence, so I will only focus on cadence. So if you are talking about the synopsis or LT space or anything, that after design specification you go for schematic design. If you talk about cadence, so in a cadence virtuoso you have a schematic editor window. In a schematic editor window you will design that circuit. Okay, just like you have a common source amplifier, so you use a VDD, you have a user RD as a resistance, and you are using a one NMOS, and where that VGS is varying, on that you will set the operating point and find it, okay, where the MOSFET in saturation and where you can put it. And after that you will provide the small signal voltage at the input side, and you find the large output voltage. Okay, that V out by V in your gain. So here you have a schematic design. On the schematic design you will design the schematic on the schematic editor window. After the schematic editor window you will go for simulation. So once you go for simulation, that simulation means what? Means you are simulating the data. Okay, you have a schematic and this, or you can think you have a schematic, let you have a CMOS inverter. After the CMOS inverter you are simulating. Okay, so on a simulation you have a what, that you have a DC analysis, you have a AC analysis, you have a transient analysis, you have a lot of analysis. Just like in a LT spice we have a DC analysis, transient analysis, AC analysis, stability. Okay, lot of operating point, lot of that analysis you have. So you will go for that spectre here, that is cadence spectre. So on the spectre you will go for that, and here you have a ADE, that is analog design environment assembler, yeah, explorer. Okay, you have a assembler or explorer. On the basis of that you will simulate either as per the requirement. That circuit have a requirement of DC analysis, you go for DC analysis. If you have a requirement of AC analysis, you can go for AC analysis. Okay, what will be result possible by the DC analysis, AC analysis we will talk later. The DC analysis will work for some reason, AC analysis for some reason, transient analysis for some output. Okay, so every analysis have a some specification. On the basis of that you will define your result. Okay, and after this simulation you go for specification meet. Okay, let you are designing op-amp, you design the schematic and simulate it on the spectre or the cadence spectre by the help of analog design environment assembler or explorer. After that you have a specification meet. Okay, so that as per you have a specification, after the simulation you will check it is correct or not. Means the gain is okay or not, the slew rate is okay or not, the bandwidth is okay or not. If it is not okay you will change something, that you will tune something W by L, you will tune VGS, you will tune something the feedback concept. Okay, as per the requirement, as per the design specification you have, you will change something, you will put resistance, you will put capacitor, or you will check something. Okay, on the basis of that you will find it. Okay, okay, the specification will meet. If the specification will not meet, you will go for the again for schematic design. If the specification meet, means that this is the part of analog circuit designer. Analog circuit designer work in this domain. The specification will meet, they will go for layout designer. Okay, after the specification meet, that copy will be sent toward layout design. The schematic will be transferred to a layout designer. So as you know that IC is not a schematic. it's a layers, that is base layers, that is N well, P implant, N implant, OD. Okay, lot of things are here. Okay, so that layout, just think in a way ki the conversion of schematic to a pictorial representation. Okay, you have a CMOS inverter, you have a PMOS, you have a NMOS, and the input is connected, you have VDD, you have VSS, you are taking the output. So this is a schematic. But once you talk about the layout, you have a layers, you have a coordinate, you have a database on the basis of that. So after the specification meet, we go for the layout design. In a layout, we will design the layout on the basis of that instance, or you can go for the custom. That what is the meaning of custom? Full custom layout means you are designing a layout also. You will design for everything like PMOS or NMOS, everything you are designing from the base layer. And if you talk about semi-custom layout design, they can call standard cell just like a PMOS, they can call, or NMOS from the GPDK or from the TSMC as per available. Okay, they can call. So most of the company are working in a semi-custom layout design. And whenever your requirement of highly precision, let you are working in a ISRO or a DRDO, okay, where that, or medical line, so where we will use a full custom, everything we will design. Of course it will take time, of course it will take cost, but that will be a perfect output. Okay, once you talk about semi-custom means you have a something, you are using that layout for your circuit, okay, for your conversion from circuit to layout. Okay, so semi-custom is good for a market purpose. But if you are talking about a medical purpose or a defense purpose, always we prefer a full custom layout. Okay, so that is a way you can understand. Okay, so after the schematic design, we will go and simulation specification meet, we will go for the layout design. The schematic is converting to a layout, the pictorial representation in terms of base layer coordinate like this. Okay, after the layout design, you will go for the physical verification. Physical verification means what? The meaning is that where we are talking about the set of rule, like DRC and LVS. So in a cadence we have a Pegasus, and a Pegasus Pegasus verification system, that is called PVS. Okay, in a PVS we have a set of rule that is designed by the library. Okay, the tech node will design that some of set of rule. Let you are designing a layout, you can't design anything from that. From the base layer you can't design anything. You will be bound for some minimum values. Let you have a, just think in a way ki okay, you have a one metal route is here and one metal route is here. So of course they have a minimum spacing. The minimum spacing will be available here, that will be decided by the design rule check, DRC. Okay, and every tech node will provide this DRC. Okay, you have a set of DRC, or once you go for, okay, you have any file tech node, you can go for search at DRM, design rule manual. Okay, in a DRM file everything is written ki what is the minimum space available requirement for metal 1 to metal 1, or metal 1 to metal 2, or metal 2 to metal 3. Okay, so this set of rule is very important, and this always DRC will provide the minimum value, that is a minimum spacing. If you are using one metal layer at here and one metal layer at here, there is no any minimum spacing. Okay, but whenever you are designing the layout now, you will work in three parts, that is power, performance and area. The three part is very important, that power, performance and area. If you are designing the layout, you are arranging the transistor in such a way, कि your transistor and routing will take a minimum space. Okay, that not meaning you are using one PMOS here and one NMOS here. There is no meaning there, you are wasting your area. And if you are wasting the silicon area, of course, you will have a lot of cost. Similarly, if you are routing, okay, that route is possible in a single line. And if you are using this way as a displacement, Okay, you are using like this. Okay, you are using a different path, unnecessary path you are using. So of course it have a resistance, and we talk about in our network class, that is IR drop. Okay, so we have a power, performance and area, that is, as per area will increase, it is directly related with cost. Area increase, cost increase. If you are increases the metal routing, your delay will increase, that performance will decrease. And if you are using a higher spacing, okay, of course the power will be wastage. Okay, so whenever you are designing a layout, we will always focus on, okay, that transistor should be arranged in such a way that we will provide a minimum spacing, minimum routing space. Okay, and the arrange the transistor in such a way that you will find that minimum space. Okay, so that is the way. Okay, whenever you have a set of rule, so DRC will help you. Okay, what is the minimum space you can arrange so that there will be no problem in a fabrication. Okay, so DRC is related with your fabrication, because if you are not using minimum spacing and you avoid this DRC, that fabrication is not possible. Because if you go for the fabrication, these two metal will bond each other. Okay, so these are the physical verification that is a part of DRC and LVS. And okay, this is DRC, and let's talk about LVS, layout versus schematic. Whenever you are designing a schematic, of course you have a transistor, you have a pins, you have a output, you have a parameter, you have a device. Okay, so how can you think in a way ki how this schematic will be same as layout? Because you are designing a layout from the schematic, so it should be equal. What the meaning of the equal? It should be equal in terms of pin. Means you have a VDD, you have a VSS, you have an input, you have output. So pin will be matched. Device means you are using a PMOS. Let you are using two PMOS. So of course you in a layout also you have a two PMOS. You have a two NMOS in a schematic. So of course you have a two NMOS in a layout also. Net match means you are connecting PMOS and NMOS and PMOS and NMOS, so that net or wire, once you go for the layout, so net also match. Parameter means you are using some W by L in a schematic, that same W by L is using in layout also. So once you go for the layout LVS matching, you will match 4 points, that is pin, device, parameter or net. If all four things are matched, that means your schematic and layout is symmetric, they are perfectly matched. Okay, so that's why we will work on LVS and DRC in physical verification. DRC will help you to find it ki okay, that if you are designing by the base layer or you are using a base layer, there will be some set of rule. If you are not following that rule, your fabrication is not possible. Every tech node will provide the DRC. Similarly, if you are designing a schematic and you are designing the layout of that schematic, you should have a match of pin, device, parameter or net. All four things are matched, then that means that layout and schematic are matched each other. This is the way. Okay, and then after that we will go for the parasitic extraction, that is called quantus extraction. That when we are going for and you are designing a layout and you said that okay, the DRC LVS is okay, everything that DRC is okay and LVS is okay, so after that you will go for parasitic extraction. Of course, you in this parasitic extraction, that means there is no any physical resistance available. In a MOSFET you have a CGS, CGD and CDS in body terms also, and you have metal. In the metal routing you have a resistance. If you have a two metal in between that, you have a capacitor. So you have a resistance, capacitor, everything you have. So how you can understand what that be a value? By the help of parasitic extraction. In a cadence you will use a QRC, that is quantus RC extraction. Okay, so you will go for parasitic extraction. Here you have a some set of values ki okay, this matter, this coordinate have a this resistor, this coordinate have a this capacitor, this amount of value it given in CIW. Okay, and then you go for what, post layout simulation. Okay, so after the layout formation and extraction, after the extraction you have a all RC values you have, and you will simulate that post layout. Same for you have a some ADE assembler, means you have a test bench at that point where that you are simulating. The same test bench you are using here for a layout simulation, post layout simulation. And if they have a same output, not necessary there will be a same, they have a change of 5 to 10%. Of course they have a 5 to 10% change. Why? Because in a simulation there is no any resistor and capacitor, it's parasitic resistor and capacitor. But once you talk about layout, you have a resistor and capacitor, parasitic resistor. So let's think in a way that you are designing a CMOS inverter. In a rise time you have a delay of 120 picosecond. I'm generally saying that the value is 120 picosecond. Okay, and after the post layout, after the RC extraction, once you go for the post layout with the same values as per giving in the simulation, if you are giving the same values here, you have a difference. It may be 120 to 125. Okay, so if there is 5 to 10% changes, means 120 to 132. Okay, 120 to 132 picosecond there is a change, so we can think that is okay. If there is change from 120 picosecond to 200 picosecond, that is have a difference of 80 picosecond, so that will be too much. Okay, so that means you have your layout is not that much good. That parasitic capacitance will, parasitic extraction will affect your layout. So what can you do? Similarly, your specification will not meet. If you after post layout simulation, if specification will not meet, you will go for layout design and check it where that RC is going on, where is the high RC, what is the output difference from the simulation, from the schematic simulation and post layout simulation. Okay, you can go for the layout design or you can go for schematic design. Why I am going for schematic design? That is, layout design is okay. That layout design means that you have a layout problem, you can go for layout design. Why we are going for schematic design? Schematic design means that after the post layout simulation you have some problem in terms of delay or something values. So you can talk to the analog circuit designer, okay, there we are facing this problem, please change that value in terms of multiplier. Of course we have a finger and multiplier, we will change that. Okay, as a circuit designer we will change it. Okay, or you can say that, okay sir, you have a resistance in your schematic, please convert this schematic resistance with that MOSFET. Okay, so that the communication between the circuit designer, analog circuit designer and layout designer. So once you go for that in a last point, whenever the part is tape out, okay, that is part of GDS. Okay, so that every member is present in the room. When that all that part is done, everything is done. So last time when that just you are sending your file to the technology, means you are going that all the files are done and you are sending your file to a Silicon Valley. Okay, that time every member is present in your room and we will figure out, okay, what is the problem at here. If the problem is settled by the layout designer, that is okay. That's why experience is important. If layout designers will settle that problem, that is very good. If that is not possible by the layout designer, that schematic designer will change or tune something where that output is not changing, that simulation result is not changing, your specification meet is not changing, but they are changing something so that layout will not provide that much amount of parasitic extraction, so that layout, your schematic or your layout post layout simulation will match. Okay, so this is the panic point. Okay, after that post layout simulation, this is the panic point where that all that analog circuit designer and layout designer will settle down and try to make that okay, that specification can meet. Okay, so this is done by the analog circuit design and analog layout design, and that is lot of things here. I am just talking about the ASIC design flow. If you talk about the VLSI, that have a floor plan, placement, routing, PD, DV, design verification, DFT, all are introduced in this. Okay, if you go for the VLSI design flow, but I am here only for the ASIC design flow, that is analog circuit design or layout design. Okay, and after that specification meet, we will go for GDS, that is graphical data system or graphical design system. Okay, this file in terms of binary files, of course, binary data files. Okay, so this binary file will send to the Silicon Valley or any, like you have a TSMC, if you are designing with a TSMC, so you will send that Korea in a TSMC, Taiwan Semiconductor. Okay, so Taiwan will design this layout, okay, that IC. So this is the flow of ASIC design flow. Okay, and this is very important when you go for that any interview. So always interviewer want it, okay, where you are working, what is the meaning of that every step, you must know. You are a schematic designer or a circuit designer, that not means the GDS is okay. The circuit designer means you have one of the part from the IC. You are not designing a whole overall IC. The circuit designer will design the circuit and try in a way that your design will be provide a perfect result as per the requirement of the design specification. Similarly, the layout should be as much good, so that your layout and schematic should match, and after the post layout simulation, the post layout result will be match or have a difference of 5 to 10% maximum difference from the schematic layout, schematic circuit simulation. Okay, and then we will send that GDS file, that is binary file, and this GDS file have a what, that is coordinate. Of course, what is the meaning of coordinate? I am talking about from 2 to means from 15 minutes I am saying that, okay, coordinate, what is the meaning of coordinate? That let you have this metal. Okay, of course this have a x1 y1, x2 y2, x3 y3, x4 y4, yes or no? Hello. And it have any metal. Okay, in terms of origin, that description in such a way कि okay, the metal one is following from x1 y1 to x2 y2 to x3 y2 to x4 y4. It make a one rectangle. So that binary file have a data in terms of coordinate. In terms of data, you have a MOSFET. Okay, so everything it have, and similarly this file will be stored in a foundry, and foundry will design that IC. Okay, I am not going for the fabrication step. I think so that you must have a basic understanding of fabrication step. Otherwise, once we will go for the layout, we will start the fabrication step. That's why very important a fabrication step, that is photolithography, ion implantation, oxidation, dry oxidation, wet oxidation. Why this is important? This is not related to you, but if you don't know about the dry oxidation or wet oxidation or photolithography or masking, or you are not understanding of the photoresist, if I am talking about the metal layer and I am talking about field oxide, you don't connect it. That's why fabrication step is important for the layout designer. So if we are interested for a layout design, you must have a basic understanding of fabrication step, and lot of knowledge is available in Google. You can search it, fabrication steps of NMOS or PMOS or CMOS, anything. Okay. Okay, let's start with the MOSFET. If you have any query, we will let's check it. Please keep it very important. Everyone asks, okay, sir, or schematic design, are you square law to determine W, I, and VGS, sir? LV has to compare layout and schematic. Yes, dear. Okay. Okay, dear. Once we go for the MOSFET now, we will talk about the square law, GM by ID. Okay. method. Okay, we have a different method to determine that. Okay, so as a basic, we will firstly start with the ASIC design flow, and then we will go for the MOSFET. So MOSFET, of course, MOSFET have a categorized in a two way, that is enhancement mode type and depletion type. What is that? Firstly, meaning of MOSFET: metal oxide semiconductor field effect transistor. Means you are talking about any transistor where that it is starting from metal, then in between it have a oxide, after that it have a semiconductor, means field. So you have a metal, you have a oxide in between this, after that you have a semiconductor. So metal, oxide, semiconductor. So this is the representation of MOSFET. Okay, and we think in a way that we have a two type of MOSFET, that is enhancement type or depletion type. Enhancement, the name suggested. What is the meaning of enhancement? The enhancing, you are enhancing something, means you are enhancing about the channel. The enhancement or depletion both are related in terms of channel. What is that meaning channel? We will discuss after that slide. Firstly, understand enhancement means enhancing the channel. You are designing, you are fabricated the channel. Enhancement by the help of gate to source voltage. By the gate to source voltage, you are enhancing the channel. Means I can say that if gate to source voltage is 0, there is no channel, the channel is not present, and the current is 0. So initially no channel is present in enhancement mode type. If you talk about depletion type, the depletion means depleted. Depleted means wash out. Okay, why? So depleted, but the depletion means that it already have a channel. The channel already present here. If I am talking about VGS equal to 0, if VGS is 0, the current is possible by the depletion type MOSFET, because the channel is present here. If I am talking about enhancement mode type MOSFET, that VGS is 0, the current is 0, because the channel is not present. What is that meaning of channel? Let's start with this in a way. Enhancement mode or depletion mode. Okay, so enhancement mode means what? You have a MOSFET. I think you know about the cross-sectional area. Okay, this is the 2D cross-sectional area. Okay, and I am designing in a way that this is a NMOS. Of course, this is P substrate. In a P substrate, you are implanting the N. So this is become N plus, and this is become NMOS. In a P substrate, you are implanting the N type. So it become NMOS. In N well, you are implanting P implant, P diffusion. So it become a PMOS. Okay. So in a P substrate, you are implanting, you are diffusing that N plus doping concentration. So this is the way, and of course you must have an idea about it. Okay, ion implantation or diffusion. Okay, so I am not going here because this is that will be a part of that is EDC. Okay, so I am not going here. I am just talking about that this is NMOS. In this NMOS, you have a P substrate. In the P substrate, you have a N plus. Okay, and MOSFET is a symmetric in nature. If you are looking this MOSFET, if you are looking from this point, they are symmetric in nature. So MOSFET is a symmetric in nature, and that have a V1 and V2. I am not writing source or drain because I am saying that this is symmetric in nature. So V1 can be a source or V1 can be a drain, V2 can be a source or V2 can be a drain. It will decided by the power supply. Okay, and the N plus and N plus is not connected to each other. Means there is no channel to form that current. Current is always possible from V1 to V2 or V2 to V1. If the current is possible by the body, that is called leakage current, that is unwanted current. So whenever you have an enhancement mode type, the enhancement mode type is representing that there is no channel. This is metal, this is oxide, that silicon dioxide. Okay, and after the silicon dioxide you have a silica, that is field. Okay, and metal oxide semiconductor. And enhancement mode, the channel is not connected. Similarly, if you talk about depletion mode, metal oxide semiconductor, the channel is connected, n plus are connected, the channel is already present. That is called depletion mode MOSFET. And that very basic part, both are symmetric in nature, everything is same. So how can you understand in terms of symbol? If you have an enhancement mode, the representation is like this, the channel is not find out, so that this is the way, this is dot dot dot. If you have a depletion type, this is the channel is already present. This is the way you are representing the MOSFET. Okay, this one is enhancement or this one is depletion. And once you go for the cross section, the channel is already present, channel is not present, that is called as enhancement or depletion respectively. And if you talk about MOSFET, MOSFET have a gate, source, drain, body. So gate and body is fixed. The gate terminal is fixed, body terminal is fixed. But if you talk about source or drain can be anyone, V1 or V2 or V2 or V1, anyone can be source, anyone can be a drain. It depends on the power supply. You can design a MOSFET in a same way, okay, this V1 become a source and this V2 become a drain, or this V1 become a drain or this V2 become a source. Why? Because this is purely symmetric in nature. If you are looking this. Okay, so this is the way, that is called N-channel enhancement type MOSFET. And this is metal oxide semiconductor. This is metal, this is oxide, this is semiconductor. In a depletion mode MOSFET, you have a gate, you have oxide, you have a semiconductor. In this, you have a channel already present. So MOSFET, enhancement mode type MOSFET is behave like a switch. Why? Because the channel is not presented. On the basis of gate to source voltage, you can form the channel. So it can be switch on or switch off. But if you talk about depletion mode MOSFET, it is behave like a resistance. You can control the current flow. Okay, that have a resistance, that channel resistance is always present here. Okay, and what is the meaning of depletion? If you are using a NMOS as a depletion MOSFET, you are reducing your VGS in a negative side. The current would be zero. The channel is depleted. That's why it is called depletion. The channel is depleted once you going where VGS is lower, below negative, 0, -1, -2, where that current will be 0. But if you talk about VGS is equal to 0, the VGS is 0, the current have a, that ID will be flow here. But here that the channel is not present. For the forming the channel, you should have a VGS should be forming the inversion layer. How it will be formed, we will discuss. But firstly, understand about the enhancement mode or depletion type MOSFET. And 99%, if you are working in analog circuit design, you never found the depletion type MOSFET as a circuit design. In a circuit design, you are not finding this because that you are not control as much current. Of course, what is the meaning of electronics? Electronics means you can control the current flow. You are studying about the flowing of current, of the controlment, how you can control the current. That is the electronics there. Here that channel is already present. If you have a VGS 0, the current is flowing on. Okay, but here is VGS 0, this MOSFET is behave like a switch off. There is no current. So 99% we will use enhancement type MOSFET, or I can say that in your journey, in your life of that analog circuit design, you will face that this MOSFET only. You will never face this depletion mode MOSFET. Okay, that is current bias you can use. Okay, that current mirror you can design with that depletion mode, but we always prefer enhancement mode. Okay, we always focus on enhancement. The in a depletion mode, you must basic understanding the channel is already present, nothing else. The channel is already present. At VGS equal to 0, you have a current. At VGS is equal to 0, the current is not flowing. Yes, is the way. Okay. Okay, so I am designing one enhancement mode type in a 3D structure. This is not a good structure. Okay, just think in a way. Okay, that this is P substrate and you have an NMOS. And I am designing in such a way. Okay, this is P substrate and this is N plus and N plus, and this is contact for a source or drain or source. Okay, and this is your gate terminal. This is your gate terminal. And make it, this is one is the body terminal, any one is the body terminal. Yes, it is the body terminal, that is P plus. Okay, this is the body terminal. Okay, and if you are looking this a circuit in a 3D view, you can think in a way, okay, this N plus have a diode with the P sub. If you are looking this N plus and P, always whenever you have a P and N, the diode is present. Whenever you have a P and P, that BJT will form. Here you have a P and you have a N, the diode is present. P and N, always you have a diode is present. So if you are looking in a 3D view, the diode is present at this region, at this region, at this region, at the bottom side, everywhere. If you are looking in a FCC format, so there is no diode is present in the topmost side. If you are talking about the bottom, left, right, backward, everywhere you will find the diode. So there the diode is not present in the upside. Rest of them, whenever you have a P and N connection, the diode is present. Okay, so this is the way that you can understand that diode is present in this. And we don't want the leakage current. If you don't want the leakage current, means the diode should be reverse bias. If you don't want the body current, the current should be possible by the source in between the two channel, that N plus and N plus, in active area between. In between active area only you have a current. If the current is going through the body, that is called leakage current, that is unwanted current, that is a wastage current. So how can you avoid it? So this is diode, and if you make the diode in reverse bias, so of course this diode is behave like an open circuit. So that's why in NMOS, the body terminal is connected to a lower supply. Why? This is P, this is a diode. Yeah, this is a diode, and you have a V1 potential, let this is Vx or this is Vy. If I am putting Vx is a lower supply voltage in your IC, let you have a IC have a different potential, let VSS1, VSS2, VSS3. I am using a minimum voltage at the body, at this side. The minimum voltage is possible at the body. That means the body is lower voltage, have a lower voltage that is possible in the circuit design. Let this is VSS. Okay, let this is VSS. If this is VSS means ground, and this can be anything, of course it should be greater than 0, because that's why I am putting this is ground, that lower supply at this point. So that means Vi should be greater than this point. So that means this diode is always a reverse bias. That means there is no current in a body. So in NMOS, always we prefer the body have a lower potential. Similarly, if you talk about PMOS, that is a cross-sectional views like this. This is P substrate, this is N well, This is P plus and this is P plus. This is metal, this is metal, this is metal. Metal oxide semiconductor. And of course the N-well, that PMOS is possible after in N-well only. And this is P sub. That is P substrate. Okay, and this is N-well. So if you are looking this is P and this is N. Yes? Is it okay? So this is P and this is N. The body terminal is N. The body terminal on PMOS is N-well. So in a PMOS we always prefer the body terminal is always provide the higher supply, that is VDD. If you are designing a PMOS, I am designing in such a way, the PMOS, that don't think this is depletion, this is enhancement. Always prefer this. Okay. This is PMOS, the body is always have a higher supply, that is VDD. If this N have a higher supply, means 100% the diode is reverse bias, means the leakage current, the body current is 0. I am not going for body effect there. I am just giving a basic understanding. We will talk about body effect in a second order effect. I am just giving the basic understanding why we are going for body in a PMOS in a higher potential and why in NMOS a body is a lower potential. Whenever the question asked in an interview, always explain in such a way ki okay sir, we have a diode. In the diode, this diode is a that N-well, and in N the body is N-well. In N-well, if you provide the higher supply, that is possible in a analog circuit design. Let you have a VDD1, VDD2, VDD3 and VDD is a higher supply. I am putting at here that higher supply. If I am putting that higher supply here, that means this diode is purely reverse bias, and this is reverse bias, that means the leakage current is 0. We don't want any body current. Okay, that is not part of that. Of course it have a BJT also. In a CMOS you will find the BJT, that is called latch up. Okay, we will discuss when we will start the layout. Okay, but till now you must have a basic understanding in terms of schematic. Okay, why we are taking the PMOS body is always to VDD, why always taking the NMOS body to VSS. If I am not using that body is not connected to VDD and body is not connected to VSS of the NMOS or PMOS, of course that have a difference of VSB, or they have some effect of body voltage, and if they have a body voltage effect, it have some changes in the ID also. Yes, is it okay? So please understand this basic part firstly. Okay, so firstly understand the cross-sectional view, that is the PMOS. In the PMOS you have a inside P substrate you have a N-well. Okay, just I want one question here. Okay, I am giving one question here. Why always taking the P substrate? That overall I see why that black body, as if you go for the cadence tool, that black body is present. Okay, why this is P substrate always? Why always we prefer P substrate? Why not N substrate? Yeah, N-well. Why always designing all the MOSFET from above the P substrate? That MOSFET always design above the P substrate. Why there? And the second question is this. This is the first question from my side. Why all MOSFET? All MOSFET means NMOS or PMOS. Design over P substrate. Why not N substrate or N-well? Second, in NMOS, I am saying that the current is entering towards like this, and in PMOS, the current is leaving from this point. One of that is current is leaving from the body, that in NMOS. So this is what? This is your NMOS and this is your PMOS. Why current is entering? Yes, towards the body. And why current is leaving from the body? Why this type of symbol? So please work on it. Okay, just define it. Okay, that's why. If you are an analog circuit designer, if you are working with me now, of course you have this type of question from me. Okay, and please work on it. Otherwise, the gap will become bigger and bigger. Okay, so please find out this type of answer. Okay, why this is happening? Okay. Let's talk about that NMOS. I am always preferring that NMOS and most of that preferring NMOS. You can take any one of that. Okay. So if you talk about this is V1 and this is V2, I am not interested for giving the name is source and drain. I am always preferring V1 and V2. And after that we will explain that why which one is V1 is source and why V1 is drain and why V2 is source and why V2 is drain. So firstly understand this is happening here. Okay. And I am providing that VGS. What is that meaning of VGS? Means you have a gate voltage and source voltage. This is the difference of VG minus VS. Okay, one of that voltage become a source, one of that become a drain. Okay, so let this V1 is higher than V2 or make it V2 is higher than V1, is up to you. Okay, make V2 is higher than V1. If V2 is higher than V1, so this have a higher potential and this is lower potential. This is one of that way you can represent the NMOS. I am saying that this is V2 and this is V1. V2 is higher potential and V1 is lower potential. And this is gate. If you are providing that VGS, or I am saying that okay, let make it both are 0, it's up to you. Okay, or I can say that okay, this V1 and this is V2. Let assume this is source and this is drain. Why this is happening, I will explain it in the terms of current. But firstly we will try to make that channel. After that channel I can explain why this is drain and why this is source. So firstly I am thinking that this is source and this is drain. Let this is source and this is drain. Okay, and I am providing that supply in such a way that VGS, this is VGS. The case first, if VGS is less than VTH or VGS is greater than 0 but less than VTH. So what is happening? You are providing the gate to source voltage, but it is not enough. This have a positive voltage here, and you have a one plate, you have a two plate, in between you have a oxide. If you are providing this potential here, positive charge, due to electric field here, it will be a negative charge. Yes or no? So there will be a formation of negative charge here due to this N plus and body. This gate have a positive potential because VGS is greater than 0 but less than VTH, that is threshold voltage. If VGS is greater than 0 but less than threshold voltage, it is providing that positive charge. Due to electric field here it is negative charge, and it should have a that much amount of negative charge, means it should have a higher negative charge. In such a way the channel will be proper in N plus and N plus. Or I can say that the minimum voltage gate to source voltage is required on the gate so that current can flow or inversion layer can form. In terms of semiconductor, I can say that what is the P substrate? In the P substrate you have a majority carrier is Na, that is holes, and this majority carrier, that is Na, have some value, that is some atom per centimeter cube. If this concentration, the majority concentration of the body, will be equal to the minority concentration below the surface, if they are equal, so I can say that this will be form a inversion layer. Please be focused here. What is the meaning of inversion layer? The inversion layer means dot. In a simple way you can say that the minimum gate to source voltage required to form the inversion layer, that is called the threshold voltage. That is very basic definition. Let's talk about the way that in terms of EDC, what is the meaning of threshold voltage. So of course in a P substrate you have a majority charge carrier, that is Na. Maybe it's not a sodium there, it's a Na acceptor. Okay, so this is a Na, that a majority charge carrier. The majority charge carrier is whole. The majority charge concentration Na have a this much area. In this much area the concentration of holes is equal to the minority concentration. The minority concentration of the P substrate is N, that doping, that electron. That electron concentration is same in below the surface. That means it is called an inversion layer. Just think in a way, okay, you have a this much area for some concentration, and you have a this much area for that concentration. You are thinking a volume per centimeter cube, and you find it what is the concentration here. Similarly, I am finding, okay, this much area volume per centimeter cube, here is the Na, that is whole concentration. Similarly, this concentration is equal for electron at that much space only. So this will form an inversion layer. So a minimum voltage, minimum gate to source voltage required to form an inversion layer, that is called the threshold voltage. This is the very basic definition. In the second definition you can say the minimum voltage required to gate to source voltage, so that majority concentration of the body can be P substrate, can be anywhere. The majority concentration of the body is equal to the minority concentration below the surface. If they are equal, so you can say that this will be an inversion layer. Okay, so this is the VGS greater than 0 and less than VTH. Whenever VGS is less than 0, greater than 0, less than VTH, the channel will not form. The ID is 0. Or in terms of picoampere. Okay, once that VGS is greater than VTH or greater than equal to VTH, the channel will form. This channel is formed here, and this channel is formed. I am saying that V2 is higher and V1 is higher. If this voltage is 3 volt, let this is 3 volt and this is 0 volt, this V2 is higher and V1 is lower. If this is higher voltage, this is higher potential, what is doing? This positive terminal is attracting this negative charge or not? this positive terminal is attracting this negative charge, and the attracting of the charge from what? From this point to this point, this path to this path. So that means that sourcing of the electron is this part, this path is sourcing of electron, and it is draining that electron. This terminal, that this V2 terminal is draining the electron, it is accumulating all the electron and make that following the current, because this have a positive terminal, and this positive terminal is higher than this terminal voltage. So this positive terminal is attracting this electron, and this point is forcing this electron. So this is behave like a source, because forcing the electrons towards this point, that is called drain. It is draining the electron. So that if you have a higher potential, that V2 is higher potential, so in NMOS always higher potential is drain and lower potential is source. If you have a V2 and V1, if V2 is higher than V1, so this is always a drain and this is always a source. In NMOS, this terminal have a higher, this node have a higher voltage as compared to this. This means this will accumulating this electron, these all electron from this channel, and electron is moving in a such path. So current will be flowing in this direction there, and always current flowing higher potential to lower potential. Higher potential is 3 volt V2 and lower potential is V1. So current is flowing from drain to source like this. This is the way. Okay, so we will explain in our next class, and tomorrow we will discuss ID versus the input characteristic and output characteristic. I will try to cover this part as I can, and after that we will design that in a cadence virtuoso. We will start cadence virtuoso, where we will simulate what will be the graph of ID versus VGS, what will be the effect with the help of W by L, what is the DC sweep, what will be the operating point, how can you determine the voltage of the different node, okay, what will be the region on the basis of VGS, okay, everything we will check on the cadence virtuoso. But firstly you must have a basic understanding there. Okay, so tomorrow we will start from this point where VGS is less than VTS, the current is 0. Ideally it is 0, but practically it have some current, that is picoampere current or nanoampere current. And once that VGS is greater than VTH, you will, that current, this VGS is greater than VTH means the channel is formed. The current will be depend in terms of V2 and V1. Okay, so VGS will form the channel. Our current is defining in terms of V2 and V1. Okay, so channel is formation by the VGS and current is forming by the V2 and V1. So that's why, and that MOSFET is called as voltage controlled current source. You are tweaking this voltage and you are finding the drain current. That is called voltage controlled current source. Okay, so MOSFET is a voltage controlled current source, BJT is a current controlled current source, and op-amp is a voltage controlled voltage source. We will discuss further, but be focused at the basic part firstly. Okay, so please cover this part and please find out what will be the answer of this question. Okay, why all MOSFET design over the P substrate? That is the first question. And the second question, why in NMOS body current is towards that body, and in a PMOS why current is away from the body. Okay, so please work on it in the both question, and tomorrow we will go for ID versus VGS and some current equation and understanding the region of operation, and then we go for that cadence virtuoso. Okay, so thank you so much everyone, and please work on it.